Physical picture of the curl. First of all, what is curl? The curl of a vector field is a vector which describes the local scale circulation of the field, but it doesn't describe the circulation of the field on the macroscopic scale. So, for example, if you have a field, a vector field that looks like this with decreasing magnitude as 1 over r, this may be curved, but it has zero curl, whereas a straight lines that we see on the macroscopic scale for a field does not imply a zero curl. It may be a non-zero curl, and we're going to demonstrate how that is so in a minute. Now let's start with a vector field which is on the xy plane, so it has x and y components. How do we write the curl of this vector? Well, using our subscript summation notation, the partial derivative with respect to xi, ei hat, that's my gradient operator, curl crossed with the vector v, which is vj ej hat. So this vector is written in Cartesian coordinates, and using the cross product here, I have the partial derivative with respect to xi, del xi, vj, ek hat, epsilon ijk. So epsilon ijk, the ith component of the first vector, jth component of the second vector, and ek hat direction. That's how we do the cross product. So that's the curl. It's a cross product with the gradient operator. So we can see that for this case, the curl of our vector v, curl v, is going to be equal to, now if I is equal to 1, then I have derivative with respect to x. So x1 is x in Cartesian coordinates. Now then j is equal to 2 gives me vy, and k is equal to 3 gives me ez hat epsilon x y z, which is plus 1. And then for x2, I have del x2, which is y, del y. And this time, j is equal to 1, so vx. And then I have k is equal to 3, ez hat, epsilon y x z. This is going to give me a minus 1. Okay, so because there is no z component of this vector field, I only have this term, and the curl is going to point in the z hat direction. So this is going to give me curl of v, curl of this vector v is equal to the derivative of its y component with respect to x minus the derivative of its x component with respect to y in ez hat direction for a Cartesian coordinate system. And if you remember, if we do this with the determinant, the fact that the z component is equal to 0, the crossing out the first row and the third column, we only have the non-zero result from this term, which is going to give us del x vy minus del y vx. Okay. So this is how we do the curl for this vector. Now I want to look at path. So I have a closed loop here, C, and around point x0, y0, I'm going from x0 to x0 plus delta x at y0, and then I'm going from at y0 plus delta y, going back from x0 plus delta x to x0. This is C1 and C3 here. And also I'm moving on the y-axis in opposite direction. So this is going to give me the closed path line integral. So we will be performing the line integral dr dot v and along this closed path, which means we're doing C1, C2, C3, and C4. So let's start with C1. So integral C1 dr dot product with vector v is, so I check my limits along C1. I'm going from x0 to x0 plus delta x. So x0 to x0 plus delta x. And my displacement is in I hat direction, dx I hat, dot product with the x component of the vector I hat plus y component of the vector j hat, and it has no z component. So this gives me integral from x0 to x0 plus delta x dx vx. Okay, now what about the behavior of vx in the vicinity of x0, y0? So vx is, y is fixed here at y0. So using Taylor series expansion, first I evaluate it at x0, y0. Then I take the derivative with respect to x, del vx del x. Evaluate this derivative at x0, y0, multiplied by x minus x0. This is my Taylor series expansion, the first two terms. And if I substitute that into my integral, so this is going to give me integral on path C1 dr dot product with the vector v is vx at x0, y0. You can see here this term is a constant, so it will come out of the integral, and the integral will give me a delta x plus the second term, integral from x0 to x0 plus delta x dx del vx del x evaluated at x0, y0 multiplied by x minus x0. So this is going to give me the first term, vx x0, y0 evaluated at plus delta x. The integral over the x dx will give me x squared over 2, but evaluated between x0 plus delta x and x0. This integral just gives us 1 over 2 del vx del x evaluated at x0, y0 multiplied by delta x squared. Okay. So this integral gives me x squared over 2, which is this term, evaluated between x0 plus delta x and x0. And x0 times x will give me, this integral will give me x0 times x, which will be giving us x0 times x0 plus delta x minus x0 square. So basically doing this calculation, we find that this is the contribution from this term. Okay, now for the path C3, if I consider the top path here, which is located at y is equal to y0 plus delta y. So I'm continuing this calculation now for C3. The integral over the path C3 dr dot v is integral. Now I'm going from x0 plus delta x back to x0 dx Vx, and the x component of my vector field at as a function of x, but at y0 plus delta y, is approximately, using the Taylor series expansion again, the vector field evaluated at x0, y0 plus the derivative with respect to x evaluated at x0, y0, x minus x0, plus the derivative of the x component with respect to y evaluated at x0, y0 multiplied by y minus y0, our delta y. Okay, now continuing with this calculation here, we have along the path C3, dr dot product with our vector field V is Vx component evaluated at x0, y0, delta x plus x0 plus delta x, x0 dx, del Vx, del x, x evaluated at x0, y0, x minus x0, and then plus integral from x0 plus delta x to x dx, derivative of Vx with respect to y, del Vx del y, y minus evaluated at x0, y0, y minus y0, and everything here is evaluated at y is equal to y0 plus delta y, right? Because that's where we are on this path. Okay, so this integral over the path C3 gives us dr dot v now you can see that because of the direction here going from x0 plus delta x to x0, actually here we have for this integral a minus sign, because this is in the direction of minus delta x, and then this is going to be minus Vx x0 y0 delta x, and then this integral gives us minus 1 over 2. The minus sign comes from the direction of the integration. Del Vx del x evaluated at x0, y0 delta x, and then we have minus del Vx del y evaluated at x0, y0 multiplied with delta x delta y. So combining these two results along these two paths, C1 and C3, we find integral over C1 and integral over C3 adds up to minus del Vx del y evaluated at x0, y0 delta x delta y. Why? Because the first two terms here were already observed on this one, and they cancel out. So only non-zero term in the summation comes from this term. Okay. Now, if we continue with this exercise for the path C2, integral over the path C2, dr dot product with v. Now, what is happening on path C2? We are going from y0 to y0 plus delta y. X is constant at x0 plus delta x. So along this path, the integral is from y0 to y0 plus delta y dy. Now, doing the same thing we did in the other two paths here, we expand the y component of the vector field around x0, y0. So that's our first term. And then we have del vx, del x evaluated at x0, y0 multiplied with x minus x0. And then we have, this is a y component, del vy, del y y minus y0, and this is to be evaluated at x equals x0 plus delta x. Okay, so performing this integration, we find integral over the path C2 dr dot product with v is equal to, the first term is a constant vy x0, y0, integral over delta dy gives us from y0 to y0 plus delta y. The second term, del vy, del x at x0, y0 is a constant that comes out of the integral. And evaluating this at x equals x0 plus delta x, we obtain delta x, and the dy integral gives us a delta y. And then we have 1 over 2 for the y integral, del vy, del y, evaluated at x0, y0, multiplied with delta y square. All right. And similarly, we can do the same exercise on path C4, which is now the opposite order for the y integration, dr dot v, and x is evaluated at x0. So we're going from y0 plus delta y back to y0 dy. Again, our Taylor series expansion, vy at x0, y0 plus del vy, del y at y minus at x0, y0 multiplied by y minus y0. We don't have the x term here because x is fixed at x0. So this term gives us, because of the change in the direction of integration, minus vy x0, y0 delta y, and minus 1 over 2 del vy, del y, evaluated at x0, y0, multiplied with delta y square. All right. So if we combine C2 and C4 the way we did with C1 and C3, we find the following. So C2 plus C4 gives us del Vy del x evaluated at x0, y0 multiplied with delta x, delta y. So therefore, we can now write our final answer for the closed path integral over this path C, dr dot v is actually del Vy del x minus del Vx del y evaluated at x0, y0 multiplied by delta x and delta y. Okay, and if we look at the limit as c goes to 0, the closed path integral dr dot v. So now this is going to be a microscopic integral. This is going to give us, we can see here, we have the z component of the curl of v as our first term. And delta x delta y is the area, so it's the limit as the area goes to 0, the area integral dx dy. So the area d sigma z is dx dy. All right, so we find that C is the contour that encloses S, and d sigma z dx dy is the differential area. Therefore, the z component of the curl of vector v is the limit as the contour C and the closed area S go to 0, closed path integral dr dot v divided by the area d sigma z. So therefore, now you can see that the meaning of the curl is really what we have suggested here, the local scale circulation of the field. So it's describing the local scale circulation of the field. It's the closed path integral over the contour C dr dot v divided by the area of the loop created. That's our definition of the curl. Okay, so our conclusion is that the z component of the curl v at a point is the line integral of v on a loop around that point divided by the loop area in the limit the loop area goes to 0. So that's our physical understanding of the curl. Now let's go back to our previous statement. So here is a curved vector field, and here is a straight vector field. So this vector field, even though it is curved, it has a 0 curl, and even though this one is straight, it has a non-zero curl. So let's see how that works. So let's consider this one now. We have the magnitude of the field dying off as 1 over r in r hat direction. So here are our polar vectors, r vector and theta vector. And the area, differential area in polar coordinates is r dr d theta, which is the differential area here. And we have the r component of the vector field v decaying as v over r with radial distance from the center. Now, if I take the closed path integral over this contour ds dot v, going from r0 to r0 plus delta r, here I have from the dot product, this has to be the r component of the vector field, the radial component. And then I have going from r0 plus delta r to r0 drvr. Then I have going from theta to theta plus delta theta r d theta v theta. And then I have going from theta plus delta theta back to theta r d theta v theta, the tangential component of the vector. Now the tangential component of the vector is 0. It only depends on r, so I can get rid of this part here. So this part is 0. And for this one, because the integral of dr vr, which is dying off as 1 over r here, we have basically these two canceling each other because it only depends on r. So this is going to give me 0. You can see that since the vector field v is a function of r only, so the increase in delta r, r0 to r0 plus delta r increase is compensated by 1 over r dependence. Okay. So if I look at this example, now my differential area d sigma is dx dy, and the integral over the blue path plus the integral over the red path now is not equal to 0. Why? Because since I find that the magnitude of the vector v is different along the blue path and along the red path. So therefore, because of this magnitude variation along these in the y direction here, on the y-axis here, if I consider these two, they do not cancel out the way it did for the previous example, because the magnitude of the vector is different. Actually, it's higher here, and it's going to be lower here. So you can see that the vector magnitude is a function of y, but I'm going on the x-axis and having different magnitudes for the vector field on the y-axis at these two different points and performing the integral over a variation in x, I would find a non-zero curl. Okay, so this basically demonstrates that the macroscopic view of the curvature of the vector field actually doesn't say anything about the curl at a specific point in space. Okay, so we have talked about the physical picture of the curl, and we have stressed the fact that the curl of a vector field describes the local scale circulation of the field, and it doesn't tell us about the curvature of the field lines on the macroscopic scale. So we've demonstrated that with a vector field on the xy plane, its curl is going to be del vy del x minus del vx del y in z hat direction, written in Cartesian coordinates. Then we have taken a differential area, delta x times delta y is going to become a differential area dx dy eventually. And we perform the closed path integral dr dot b by considering our vector field in the vicinity of x0, y0. And for example, along the path C1, x is varying, but y is fixed at y0. And for x equals to x0, we get the first term in the Taylor series expansion, and then derivative with respect to x minus x0 gives us the second term. If you had here del vx del y, because y is fixed at y0, you would get a 0 from that term. Okay, and then we perform the integration and we get this result. And then we repeat it for C3, the same exercise, except this at this one, we have y is not equal to y0, but y0 plus delta y. So therefore, we do have this term, and that gives us a delta y. And then we're careful with the order of the integrations for the paths C1 and C3. For C1, it's x0 to x0 plus delta x. For C3, it's x0 plus delta x back to x0. And repeating this procedure along C2 and C4 also, we find that the closed path integral dr dot v actually gives us the z component of the curl of v. So in the limit c goes to 0, or in the limit this area goes to 0, it becomes a differential area. We can write this equation. C is the contour that encloses an area S, and the area, differential area, is dx dy. So we reach this conclusion for the curl of a vector field, and basically it tells us that at a point in the vector field z component at a point is the line integral of v on a loop around that point divided by the loop area. In the limit, the loop area goes to 0. Then we go back to our previous examples. Here is a vector field that does have a curvature, but because of the way the magnitude varies as 1 over r, so it decreases as we go in r, the two integrations from r0 to r0 plus delta r and delta r and r0 plus delta r to r0, actually the increase in the area is compensated by the decrease in the magnitude, so they cancel each other, and we can give this can give us 0. Now, and it doesn't have any tangential component. In this case, when we go from x0 to x0 plus delta x and x0 plus delta x to x0, because we have different magnitudes along these two paths here, they do not cancel out, and that's due to the fact that we have a variation of the magnitude in the vector field that is basically giving us a non-zero curl. So we cannot reach the conclusion that the curl is 0 just seeing that we have straight lines in the vector field.